All right, folks, in this video, we're going to be talking about the representation of graphs. Now, these graphs are a lot different than what you're used to, so make sure you're paying close attention and taking notes. Here we go. All right, so here's our first example of a graph. All right, notice that is something that you've never seen before in your entire life for the most part. Basically, what this graph represents a story. So let's say that these five, one, two, three, four, five, let's say that these five uh, points here represent the players of a basketball team. So players of a basket. All right. So these represent the players of a basketball team. Now, the ones that are connected. All right. So the lines that connect the two players. So basically, and again, I'm just playing the what if game. If a player is connected to another player, that means they are friends. Okay. They are friends. So just kind of looking at this example, this graph here, if a player is connected to another player, that means they're friends. So when you analyze this graph, you would say, okay, A is connected to C, that means A and C are friends. But if you notice, B is not connected to A, so that means you would say they are not friends. All right, very simple concept. Now, now, if I was to ask you a simple question of, hey, which player is the most friendly, or which player is friends with all the players on the team, you would say, oh, C, because C is connected to all the players. All right. Now, this example brings us to what is called adjacent vertices. Now, adjacent vertices are very similar to like the example I gave you, and they are very simply adjacent vertices are points that are connected. That's it. So adjacent vertices are points that are connected. So again, if I was going to give you a very simple example, if I would say, hey, player B and E, are they adjacent? You would say yes, because there is a common line between the two. All right. Now, construct a graph for the following sets of vertices. All right. So now, a little bit of terms here. Vertices right here, this means points. So the vertices means points. The edges mean lines. All right. So when you create this, now what I recommend when you're creating a graph, always kind of create the graph in a more of a circular pattern. So it'd be like A, B, make sure your points are kind of spread out. C, D, E. Now everyone's graph is going to look a little different depending on where you put your uh, vertices here, but all the connections should still be the same. So like for example, when it talks about edges, and this is very similar to a line segment. So AB, very simply what you would do is you would connect AB. Next would be AC, so AC right there. Next would be AD, AD there. And next one will be BE, so we're connecting E to B. Very simple. So that's what your graph would look like. Now, remember, your graph would represent something. Now, we just don't have the story, so we don't necessarily know exactly what these represent, but it's basically a graph. All right. Now, same concept with this one right here. So what I did here was I created a matrix, and what you're going to do is you're going to create a graph based on the matrix. Now, let's kind of break this down a little bit. First off, the points that you'll be using, you can just look either down a column or down a row, A, B, C, D, E. So again, creating the little circular pattern here, C, D, E. Okay, so again, as you're creating your vertices, make sure they're all in a circular pattern. So first off, you are going to read this matrix by rows. Okay, so the first thing, if you notice, when you're reading this matrix, you have a 0 for an 8A situation. Okay, now that might be a little confusing, so let's go to this. Notice you have A and B. See how there's a 1 between the A and B? So you would draw one edge between A and B. Notice that A and C there's a 0 when you line up A and C. That means A and C would not be connected. There would be no line shared. A and D, no line shared. But notice A and E. See, there's a 3 there. So that means you're going to have 3 actual lines, like so. All right. Then you move down to the next line, and you do the same thing for B. Now, here's the thing to notice, and that is, notice between A and B right here. See this one right here? It's already been drawn. So if it's already been drawn, you almost like just disregard that. All right. So if you keep reading, A, B, and C. All right, B and C, that has not been drawn yet, so we draw a line. B and E, it's already been connected. All right. Now, let's keep going. Let's go down to C. So A and C. So A and C, 0. There's no lines between them. C and B, notice that there's a line here, but notice we already drew that line. So that kind of gets disregarded. C and C, nothing. C and D, oh, there's a 1 between C and D, so we're going to draw a line there. C and E, there's a line. That's going to be connect, or an edge. Sorry, I keep on saying line, I mean edge. All right. Now, as you're working through this matrix, you're going to be skipping more and more. So like D and A, nothing. D, B, nothing. Oh, D and C, there's a 1 here. Let's see, D, but it's already been drawn, so we kind of just forget about it. So D and E, oh, there we go. All right, so, okay. So as you move to the very last one, most of these you're going to skip because it's already been drawn. So like A and E, notice that there's a 3 here, but it's already been drawn 3 lines, so that's gone. E and B, already been drawn, so we skip that. E and C, oh, already been drawn. E and D, already been drawn. But notice here we have an E to E situation. An E to E situation means it's leaving E and coming back to E. That makes this a loop. So what we've created is a loop. So a line that leaves one vertex goes back into the exact same. Now, it says find the degree of each vertex. Now, finding degrees is very simple. All a degree is basically, and you can kind of see it in the next example here, and that is, it's the number of edges that a specific vertex has. So basically, how many times is a line going into A? So let's focus on A, for example. A is right here. How many lines are basically, keep it simple, how many lines are touching A? Well, you have 3 lines coming from E, you have 1 line coming from B. So that is a grand total of 4. Look at B. Very simple. Don't overthink it. Look at B. How many lines are touching B? Like physically touching B, it's 3. C is the exact same way. How many lines are touching C? Well, I see 3. 3 lines are touching C. D, there's 2. Now, E is a little tricky because we have the loop. The loop touches E 2 times. So that means that this loop counts as E being touched twice. All right. So E is being touched here, here, and here. I keep on saying touch. I meant connected. So that's 3 times. It's E is connected to B. E is connected to C. E is connected to D. But notice E is connected to itself 2 times. So 1, 2, 3, 4, 5, 6, 7, 8. So you would say the degree of E is 8. All right? So this next part, very similar to what we just did. All right, so find the degrees of everything. All right? So finding the degree of A, notice that A has a loop. So A is being connected 3 times. Look at B. How many times is B being connected? This should be very mental, so C. How many times is C being connected? I think 6. D, 3 times, and then E, 2 times. That's it. Now, a connected graph, now we're going to spend a couple minutes on this right here. A connected graph means each vertex is connected. What's a good way to say it? Each vertex is connected one way or another. Okay? A complete graph means each vertex is connected to every vertex. Okay? So let's go back to the example we just did. Let's go back to this graph right here. Okay? Notice how everything is kind of connected, one way, shape, or form. All right, so like A, D, C, everything is connected one shape or form. So I kind of look at it as like a spider web. Not everything is connected to the spider web, meaning every line is connected, but it's all connected. So what you would say is this graph right here is a connected graph. All right, but it is not complete. The reason why it's not complete is because every vertex is not adjacent, is not touching every other vertex. So let me give you an example of a complete graph. So let's say, for example, I set up a complete graph. All right, so let's say if 1, 2, 3, I'm just using dots as opposed to letters, okay? So in order for this to be complete, every dot has to touch every other dot. So here, here, it's got to touch that dot, it's got to touch that dot, okay? Now this one's got to touch this. Now remember, complete means everything is touching everything else. And that one's already touching that one, all right? This is touching there, this is touching here, and it's already touching there. All right, so there you go. This would be an example of a complete graph. And the reason why it's a complete graph is because every vertex is touching every other vertex. All right? So going back to our worksheet here, we're going to go ahead and skip down to like graph number 1, 2, 3, and 4. All right? So very simply, we're just going to graph these things because I really want to kind of do the whole graph complete versus connected. All right? So A, B, C, D, and E. So A, remember, when you're creating everything, kind of create everything in a circular pattern. All right, so I'm going to connect A to B, connect A to C, connect A to D, connect E to B, and then lastly B to E. Now, question, is that a complete graph? Is that a connected graph, or is it both? Well, if you notice, everything is connected one way, shape, or form, so you would say that this is a connected graph. But because of the fact that all the vertices are not touching every other vertex, meaning like A is touching everybody, but B is not touching, is not adjacent to every vertex. So you would say it's just connected. All right, let's try this one here. M, N, O, P, Q, R, S. All right, so M and N, we're going to connect. S, R, we're going to connect. That's kind of a bad way to connect it, but it's QS, connect. SP, connect. OP. There we go. So is that connected or is that complete or neither or both? Now notice here, and that is, see how MN is kind of like floating all by themselves. M and N, these two vertices, are not connected to all the vertices down here. So you would say that this is it is not connected. All right. Now this one right here, I think we're running long on time, but we'll go ahead and do these last two here. All right. So again, when you spread out your vertices, kind of put them in a circular pattern. G, J, and I'm writing with my mouse here, so K and M. All right. So E to F will be connected. K to M is connected. F to G connected. J to M is connected. E to G is connected. And then KJ is connected. Uh-oh. Basically what we have is two triangles. So hopefully you can see it. So we have E, F, G. All these are connected. But then we have M, J, K. They're not. These two are like almost like two separate graphs here. There's two different parts to it. So basically not connected. And if it's not connected, obviously it cannot be connected or complete as well. And lastly, W, X, Y, Z. All right, let's make our connections. W to X, X to Z, Y to Z, X to Y, and then Y to, I think I missed one. Oh, W, there it is. I thought I missed one. All right, so there's our graph. Notice, are there any floating parts? Is it just one big graph? And the answer is yes. So you would say that this is connected. But also, notice that all the vertices are connected to every other vertex. So you would also call this a complete graph because every vertex is touching every other vertex. All right? So that's the basics of this lesson. So when you continue, you obviously just continue, just keep working. And that's pretty much it. So thank you for watching. Let me know if you have any questions.